Hello, my amazing students. This is Mrs. A, and we are doing 5.2, and I'm going to answer the questions that are at the end of your PowerPoints so that you can get ready for a test. And the first one is just calculating on the calculator. So I really didn't do these much because all you have to do is stick them on the calculator, e to the 1.1, and all you have to do that is go to your, oops, there you go. Go to your natural log. So you're going to go to the second here, and you're going to hit your natural log button, and you can see that the second function is your e to the x button. So you're going to hit second and then natural log, and that will give you your e to the x. Okay, I've got a glare going on in here. Okay, and then e to the 1.1 you enter there, and you get out 3.0041 blah blah blah, and you're supposed to round that to 4 decimal places, so it winds up being 3.0042. So then you can do this one and check it. I'm not going to do it for you, but it is e to the 0.21, and you should get the result being 1.2337. So now we're going to do some graphing, and I got a little bit of the glare off the board here, but we'll see. So we're going to do f of x is 4 times e to the negative x, and remember that your e to the positive x function goes like this. But when we have our e to the negative x, it's going to come and be a reflection of that one. So this one should look more like this one over here. But let's plug in a few points. Now, both of the point, e to the x and e to the negative x should anchor at the 0, 1 spot. So let's just plug in a few points to make sure that this is what we're looking at, and the 4 should be a stretch, shouldn't it? So now we're going to have x and y. If we plug in a 0, we do get out that anchor point, 1, but it's going to be multiplied by 4. So that's going to slide this one up. Then we could plug in a 1, and we're going to get a 1 over e, because it's e to the negative 1, so it's going to be 1 over e, and then we're going to have 4 times that, so it's going to end up being 4 over e. Okay, now remember, e is about 2.7, so 4 over e is a little bit bigger than 1, but it's less than 2, isn't it? So then we're going to plug in a 2. Okay, when we plug in a 2, we get e to the negative 2, which is 1 over e squared, and then we multiply that by 4, and we get 4 over e squared. Now, e squared is going to be bigger than 4, so this is going to be positive, but it's going to be less than 1. And so here we are getting smaller as we go this direction. Okay, so I'm going to continue to get smaller because every time I raise that power, it's going to flip downstairs and be a higher power downstairs, which is going to make this get closer and closer and closer to 0, but never reach 0. So let's go backwards the other way. Let's go to negative 1. Okay, when we plug in a negative 1, we get e to the negative, a negative 1. So that's going to be e to the positive 1, which is e. So we're going to get 4e, which should be, you know, somewhere between 10 and 12 probably, because again, e is 2.7 times 4, so it's going to be going up in this direction. So to plot that, we need to adjust these points. Remember, this was just e to the x and e to the negative x. So let's just take this and let's put in our little grid. Oops, that was a bad line. Let's do that one more time. Okay, so let's put in a few more specific points. So now instead of 0, 1 being our anchor point, it's 0, 4. So 1, 2, 3, 4. Okay, and 4 over e is between 1 and a half. So 1 and a half maybe. 2, and we'll say, okay, so that's 2.7 squared. So it's getting down there a little bit. and it's going to approach there. Okay, on the left, negative 1 times 2.7, 4 times 2.7-ish is going to be 2.8, 8, 10. Okay, so a little bit, 10, almost 11. So negative 1 is going to go way up there. So it's going to climb pretty rapidly in that direction. So that's a fairly rough graph, but what you need to do on these, this was pick out the right answer on these. And so this one, if you remember what or if you have gone back and looked at your PowerPoint, this one was going to be D, which looked very much like that. Okay, so the next one that we're going to do is number 4, and it looks like this. Okay, now remember, when I have a number that is greater than 0 but less than 1, it is going to be that negative X shape. It's going to be coming downward, but this one is a reflection across the x-axis, isn't it? So we're thinking that this one is, instead of coming down like this, is going to reflect somehow like this, but that's very, very rough. So let's see what it really looks like by plugging in a few points. Okay, so x, y, and I'm going to plug in a few points. So if I plug in a 0, which is always my little anchor point, I'm going to get 3/4 to the 0, which is 1. And then the negative out here is going to make it a negative 1. So that point there is a 0, negative 1. If I plug in a 1, I'm going to get a 3/4, but it'll be a negative 3/4. So it was negative 1 before, so now it is getting smaller up closer to the axis. If I plug in a 2, then it's going to become a negative 9/16. Okay, and 9/16, remember 3/4 is closer to 0.75. 9/16 is a little bit more than a half, so it is decreasing as it moves up towards the axis. So let's go in the other direction, negative 1. If I plug in a negative 1, then this is going to become 3/4 to the negative 1, or 4/3. So that's going to become a negative 4/3, which is greater than 1. Okay, so, and then if I plug in a negative 2, then I'm going to flip this thing over, and it's going to be 16/9, but it'd be negative 16/9. So now it's close to negative 2, and this does look fairly accurate over here. So negative 2 is close to negative 2, and negative 1 is a little bit over 1. So that actually looks like a fairly decent curve. And these would be our points right there. Okay, so the next one that we're going to do is the next one on the PowerPoint, and it's 5x minus 1 plus 2. We're going to f of x is 5 to the x minus 1 plus 2. Remember, these are all exponentials because the variable is in the exponent. Okay, so now we're going to, since it's a positive x, and since our base is greater than 5, we expect it to climb up this direction. However, we have a translation here, and it's going to move it up too. And so our anchor point, which would usually be 0, 1, should now be 0, 3. Okay, so this point right here where it anchors should now be 0, 3. So let's make our little grid here. So we have our x and our y. We plug in a 0. Now the 0, oh, it's going to have a horizontal translation, isn't it, too? So we've got at 0, that's going to become a negative 1. So we're going to get 1/5 plus 2. So that's going to be 2 and 1/5 at 0. So it's not going to be 3. It's going to be 2 and 1/5. My bad. Okay, so then we plug in a 1, and we get a 1 minus 1, which is 0. So 5 to the 0 is 1, plus 2 is 3, so 1/3 is really the point that I was thinking was at 0, but it wasn't. I have to plug in points. Always plug in points. All right, so number 2, so 1, 3, and then number 2, plug in a 2, I get a 1. 5 to the 1 is 5, plus 2 is 7. So this one is climbing pretty good here. So we're going to make it go a little sharper there. So 2, 7, and then let's go backwards a little bit. So let's go -1. And we got a -1 minus 1 is a -2, and 5 to the -2 is 1 over 5 squared. So that's going to be 1/25 plus 2. So that's going to be 2 and 1/25, which is smaller than this one, as we expected. And then -2 is going to be -3, which makes it 1 over 1/25 plus 2. So that's going to be 2 and 1 over 1/25. That's pretty tiny. So you can see that it is approaching the asymptote of this asymptote here would be x is equal to 2. Okay, so we'll say this is the asymptote. We'll make this nice and dotted, and then we'll go ahead and put our regular axis there. So it has an asymptote. It shifted 2 to the right. It shifted, 2 to up and 1 to the right. I can't talk today. It shifted 2 up and 1 to the right. Okay. The next one we're going to do is just f of x is 5 to the x. So it's basically simpler than the one we just did. This one should have our normal point of our anchor point there. So if we plug in a 0, we get out a 1. Okay. If we plug in a 1, we get out a 5. If we plug in a 2, we get out a 25. So that climbs rather rapidly. If we plug in a -1, we get out a 1/5. And a -2, and we get out a 1/25. So when we plug in these, we get our anchor point there. 1, 1, 2, 3, 4, 5. We can't even plot this one because it goes way off the chart, way fast. And then -1, 1/5, and -2, 1/25, and it approaches the asymptote, which is the x-axis, very, very, very quickly. So that is, again, on your PowerPoint, at the very end of the PowerPoint, this is where I'm getting those problems, because this is your test generator. And so these problems are the ones that I would probably likely put on a test. So now we'll come back with more in a moment. All right, so now we're working on number 7, which is y is 1/7 e to the x. So this is going to be your normal e to the x function with a shrink, right? Because the 1/7 is less than 1. It's going to be a vertical shrink or compression. And so this one should just be what I call flatter. It should have a gentler slope instead of a sharper slope. So we would just throw in a couple of points. And again, our anchor point is going to be 0. And then when we plug in this one, we're going to get e to the 0 is 1, but then it's going to be multiplied by 1/7. So it's going to be 0, 1/7. We plug in a 1 and we're going to get an e, but it will be an e divided by 7. And then we plug in a 2 and it's going to be an e squared divided by 7. So it's just going to have a much gentler slope. Okay, then on the other side, we plug in a -1. We're going to have e to the -1 divided by 7, which is going to be 1 over 7 times e. Okay, so 1 over 7 and e are in the denominator, and it's just going to keep on going like that. So this one is going to be our normal like this, but it's going to stay close to the axis. It will eventually go up, but just at a much slower rate. So it's going up, but much slower. So it'll look something like that because everything's being cut by 7 as it goes. All right, so it's just a gentler slope, but it will eventually climb because the exponential will grow faster than the 7. Okay, then number 8 looks like this. All right, and we're graphing it, and this is just going to be our regular e to the x function slid down 4 spaces on the y-axis. So we can go ahead, there's our x, and we're just going to go ahead and put 1, 2, 3, 4, and slide in a nice horizontal asymptote there. And then our special point will now be, instead of 0, 1, it will be 0, -3. Okay, and we can see if we plugged it in, 0, we'd get a 1, minus 4 is a -3. So 0, -3 is a point. And if I plugged in a 1, I'd have an e minus a 4. So basically everything is doing just what it was before, but it is dropped down 4 spaces. Okay, so it's going to go up like that. Okay, so general effect there. All right, so now what we're going to do is do number 9, and now they're starting. We're supposed to graph these, but I think I've graphed enough of these for you. What we're going to do is just describe what is happening from the original function, which is going to be the 4 to the x function, would be the original parent function. And now we're going to say, what is happening here with this new function here? Can I describe the transformations that are going on here? Okay, so basically, the first thing I noticed is that it is moving 3 to the right. Okay, so I'd say 3 right and 3 down. Okay, now if you look at it, this 4 is not a stretch. The 4 is the base of the exponent. So that would be just 3 right and 3 down would be the only transformations that are occurring in that one. Okay, so the next one, again, is describe the transformations. And here we look and say, okay, this is 2 is the base, and then we have an x plus 3. So that's going to move it 3 to the left. So 3 left, and then 5 down will be the transformations occurring there. 3 left and 5 down. And we have this one. Okay, now notice what's happening here. We've got our function is e to the x. Okay, and then they've got some cool things going on in here. We have a 2 times, which is going to wind up being a stretch. Okay, so we're stretching by a factor of 2, but what are we doing? Got a negative x in there. So we can see this really better if we just go ahead and distribute through that 2. So let's just take the 2 through, and we've got a 4 minus 2 e to the x. And I really like to go ahead and do that because then it kind of helps you see what you really have. So don't we have it moving up 4 spaces? Okay, so up 4. And then reflected across the x-axis. Okay, and then stretched by 2. So reflected across the x and stretched by a factor of 2. Okay, so that's what's going on in that function. A vertical stretch reflected across the x-axis and moved up by 4 units. So distribution can help you when you get something real complicated to just figure out what's going on. All right, so here we have number 12 on the back of the PowerPoints, and we have e to the negative x plus 3. All of this is the exponent there. We could put it all in a parenthesis if we wanted to clarify it, but it's all up there. Okay, so now we have a negative x, and remember a negative x is going to reflect horizontally across the y-axis, and then we have a slide. okay? And my little dyslexic brain has a hard time with these. And so what I do is I always plug in points and see which direction it's going. So when I'm looking at this, I will say, okay, what happens when I plug in a 3? If I plug in a 3, because that's what's going to make this go to 0, right? If I plug in a 3, I'm going to get my 1. Okay, so since that usually happens at 0, that I get a 1, which way am I sliding? Okay, I'm sliding 3 steps to the right, not to the left, because it is a 3. Then that becomes a -3, and that's going to make it go to 0. So it's going to be 1, 2, 3, 1. It's sliding 3 steps to the right instead of the left. One of the things you can do when you have one of these is you can actually pull out the negative sign and see it like you're used to seeing it. You can pull out the negative out front and see the x minus 3, and then your brain thinks, oh, I moved 3 steps to the right. Okay, so if I plug in a 2, then it should be what? Since I'm reflecting across the y-axis, it should be bigger. Okay, so let's plug in a 2. We plug in a 2, we get a -2, plus a 3 is a 1, so e to the 1 is going to be e. And e is bigger than 1, isn't it? So then I plug in a 1, and I'm going to get a -1, plus a 3 is a 2, and I wind up with an e squared, which is 2.7 squared. So it's definitely climbing up here. So 2 is going to be about an e, 1 is going to be about an e squared. Okay, and so then it's going to go up pretty steeply there. Okay, and then I'm going to come down closer to the axis. I plug in a 4, and I'm going to get a -1, which is going to be a 1 over e, which is 1 over 2.7. So this is declining in this direction. So that should be a fairly decent graph. So now, if we were going to describe this, we would say it is what? Reflected across the y-axis and translated 3 steps to the right. Okay, so reflected across the y-axis and translated 3 steps to the right is the correct answer, because I have the answers in front of me. Okay, the next one we're going to do is a piecewise function. All right, so you will have a piecewise function on your test, probably on your final, and so these are important. So we have the function described as this for x is less than -2, as x minus 1, which is linear between -2 and 1, and then as a cubic equation between when x is greater than or equal to 1. So I'm going to go ahead and put my graph right here. Okay, so when x is less than -2, so I'm going to just kind of make a little line. This is not really needing to stay in my graph. I'm just kind of trying to see my zones here. So I got a -2 to a 1 zone. This is not an asymptote. This is just a demarcation line here. I'm kind of breaking this up into my 3 regions of x's here. So I'm going to have an exponential on the left here, and I'm going to figure out where that is at -2. So if I plugged in an e to the negative, a -2, that's a e to the positive 2, which is going to be 2.7 squared, right? E squared minus 9. So it's going to be a little bit less than 1. This is going to have a what? This would have a vertical asymptote of -9. So it's going to drop way down here, but it's only showing what it's doing from -2 to -infinity. Okay, so basically we're only seeing the little upper tail of this thing, and it's going to be just a little bit below the axis. So since it just says less than, we'll just put a little open circle right there, just slightly negative. Okay, and since it's e to the negative x, shouldn't it be coming from down here? So we should have something that's kind of going here, and it's coming down this way, and it would be approaching an asymptote of -9, but it never gets to do that because it is stopped. It is no longer the ruler of the next domain. So we go to the next domain between -2 and 1, and it is a linear function. So what's easy to do is plug in the two endpoints. Okay, so we're starting at -2, we plug in a -2, -2 take away 1 is -3. So at -2, we're going to go 1, 2, 3, and we're going to put in a closed circle there because it's got an equal sign. And then when I plug in the 1, because it's the right-hand side of the domain, I'm going to get 1 minus 1 is 0. So 1, 0, and that one is open. So I'm going to have to erase that nice little dot and put an open circle there. Okay, at 0, and that line is going to go like that. And then lastly, the last part of the domain is cubic. Okay, so when I plug in a 1, I get 1 cubed, which is 1. So I'm going to start right here at 1, and I can put a closed bubble there, closed dot, and then 2 cubed is 8. So it's going to climb pretty quickly, right? 2 cubed is 8, and it's going to go shoop very quickly because it's the right-hand side of the cubic function, which would cross at 0. And remember, cubics have a squiggle, and I'm kind of making what it would look like, but it's only in this domain. So we have this kind of weird looking shape here, but that would be about what you have. Okay, so I'm going to show you what they have on their much prettier graph. Okay, so this is the same answer, how they've broken it up, which a much nicer, neater graph. But it really does look pretty much like what I had there. They just have nice lines. All right, so now we're doing number 14, and we are starting another piecewise function, and this one has a -2, which is a constant for its first domain here. We got the domain is -infinity to -2, and it's a constant function. So 1, 2, we're going to be coming all the way over here, and we're going to have to stop when we get to -2. So we should have put our little line of demarcation there so we know what's going on. So we're going to go, this is our first region all the way up to -2, and we're going to put a closed circle there. And the next little region is a quadratic function, x squared plus 3, which means I'm going to have my basic parent x squared function shifted up 3 spaces. So 1, 2, 3. If I were going to graph the whole function, it would be going upward from there on both sides. Okay, but I'm not graphing the whole function. I am not graphing this side because this side is entering a new domain ruled by a different ruler, and that ruler is going to be e to the x. So we're going to leave that guy alone. We're only working on -2 to 0, and between -2 and 0, this is kind of what it looks like, but we can get a little bit more detailed by just saying, okay, I'm only playing with this thing from -2 to 0. When I plug in a -2, my function becomes a 7. So I can be a little bit more specific here. Go 1, 2, 3, 4, 5, 6, 7, and so we're going to have a point there, but it's not a closed circle, it's open. So we're going to put a little point there, okay, and it's going to come down to the 3, and it's going to be a closed there. So that one will be, and then we'll just do our little gentle quadratic slope up there. And then the last region is going to be e to the x, and it is not a -e to the x, even though I just put little grids there. So I'm going to erase that one. It is a positive e to the x, and e to the x should be climbing in this direction. So Generally, wouldn't it be coming this way, crossing through 0, 1, and then going up? But this part's not in there because this is somebody else's domain there. So we're going to start right here at 1. It's going to be open circle bubble on 1 because that's greater than. And then it's going to sweep up in that exponential curve, and that's what that one looks like. Okay, and again, I'm going to show you the much nicer picture in the book. Okay, so this is the same thing. This was the original problem, and this is the answer, which is just a little bit neater than what I had. All right, so now we're going to do some investment problems, and when we're using our compounded semi-annually, quarterly, whatever it is, we're going to be using our formula is the amount after time is equal to the principal, which is the initial amount, times 1 plus R, which is your interest rate, divided by N, which is the number of times per year it is compounded, and then raised to the NT. So this is your compound interest formula. So now we're doing a problem, which is number 15 in your PowerPoint problems, that has an initial investment of 1,000. So our 1,000 here is going to be our principal, and our time is 2 years compounded semi-annually, so our N is going to be 2. Our interest rate is 10%, so we're going to write that as 0.1. So we're going to end up with 1 plus 0.1, when we move it to a decimal instead of a percent, 0.1 over N, which is 2 because it's semi-annually, and raised to the 2, and then the T is 2 years, so we'll put times 2 there, and then we're trying to find this amount that's going to come out. Okay, so this should be our formula. Now we're going to do that on the calculator and see how to properly calculate that one. So I have my calculator here. Okay, so I'm going to plug in the 0.1 divided by the 2. So 0.1 divided by the 2. Okay, and then I'm going to add the 1 to it, so plus 1. So that should be the number that I have inside the parenthesis. Now remember your order of operations. I have to do what's in here first, and then I have to raise it to the power next, and then lastly I multiply by the 1,000. Okay, so I've got what's inside the parenthesis there, and now I'm going to raise it to the 2 times 2, which is going to be the 4th power. So to raise it, I click the little caret button here. That's my raise to a power button, and I'm going to put in a 4. And then I'm going to take 1.2155 and multiply it by 1,000, which was my principal. And I get $1,215.51, which is the answer. So there's your answer there on the calculator. And of course, they're going to turn that into money, and they're going to round it to 51 cents on the end. So $1,215.51 for that one, which is what we got. Now, the next one we're going to do is also a compounding problem, but we're going to do this one quarterly. So we're going to use the same formula. The amount after time is the principal times 1 plus R over N to the NT. This is a formula that you should memorize. That is your compounding formula. Okay, so now our initial investment was $480. So we're going to plug in $480 right here in the front. We're going to turn our T into 4 because they're 4 years that it is going to be invested for. And then we're going to have a 12% interest, which means that our rate here is going to become a 0.12. And then compounded quarterly means 4 times a year. That means the n is 4, and the n downstairs here is 4. So now what I'm going to do is get my calculator and do this inside the parenthesis first, then raise it to my exponent, and then multiply it by the 480 and hope that we get the right answer here. So we have 0.12 divided by 4, and we're going to add a 1. Okay, so you should get a 1.03 inside your parenthesis, and now we're going to raise it to the 4 times 4, which is 16. So I'm going to raise it to the 16 power, and I get that. And lastly, I'm going to multiply that by 480, and I get that. So $770.26, and that's what we have. And that's the correct answer. So a very simple formula right here. You're going to make sure that you memorize that formula, plug it in, and you should be good. All right, so we're going to finish up this video with 3 more problems. This one is another one of the compounded annually problems. So this one is compounded annually, which means 1 time a year, which means n is going to be 1. We have the amount after time will be the principal, which is 1,000. 1 plus, and then our rate of interest is going to be 0.04 over, since it's annually, it's just going to be a 1, which we don't really even have to put there, but we will just for consistency. And then since the n, we have an nt over here at the end, the 1 is not going to make a difference, and the t is just 8. So 1 times 8 is 8. So that should be your formula. And when we plug this into the calculator, then we should get, let me see, okay, so this one is the annually one. So this is number 18 that we're doing. And we're going to plug in our 0.04, and that's divided by 1, so that doesn't matter, plus the 1. And so I get 1.04 inside the parenthesis. I raise it to the 8th power, and I get that, which is 1.368. And then I multiply times 1,000, which gives me $1,368.57, which is what they have on the PowerPoint as the answer. So we did it right. Okay, so now we have some word problems, and I'm going to do these with the graphing calculator, because when we got down to the end of chapter 5.2, which is what we're doing, we had not yet worked on natural logs, undoing. We were doing exponentials, not natural logs. So what we're going to do is we're going to use our graphing calculator to solve the next problem. And the next problem says, a company begins a radio advertising campaign in Chicago to market a new soft drink. The percentage of the market target market that buys a soft drink is estimated by the function. So there it is. They give you the function, and they tell you that this is the percentage, where T is the number of days of the campaign. After how long will 70% of the target market have bought the soft drink? Okay, so we're going to do this with the graphing calculator. So what we want is we want our percentage to be 70%. So we're going to put 70 equals 100 times 1 minus e to the negative 0.02t. And we're just going to plug all this in to the graphing calculator. So I'm going to go ahead and just divide both sides by 100. So when I divide this by 100 and I divide this by 100, it makes it a little bit easier to enter in. And this side is just going to become a 0.7. So I'm going to have 0.7 on the left. Okay. On the right, this goes out, and I'm going to have 1 minus e to the negative 0.02t. Okay, now if I wanted to, I could subtract the 1 from both sides, but I'm going to go ahead and go with what I have right now. I'm going to set y sub 1 as 0.7. I'm going to set y sub 2 as 1 minus e to the negative 0.02 t. So here's our calculator. So I'm going to go to my y equals button. I'm going to clear out what I already have there, so you can clear yours at the same time. Okay, so now a nice clean calculator. So on the left, I'm going to put the 0.7, or in my y1, so 0.7. And on the right, on y2, I'm going to put 1 minus e, so that's going to be second exponent. And then it's going to go negative. So negative, I'm going to use this one down here, negative 0.02 t, and close parenthesis, and so I have this, okay? And when I graph it, okay, I'm going to end up with my constant function, which was 0.7, and my other function is not showing up, which means my window needs to be adjusted. So I'm going to go look at what my window is, and I can see why my window needs to be adjusted. The last problem I did not have a good window. So I'm going to put my function back to just negative 10 to 10 and negative 10 to 10, just to see if I get a little bit better picture. I'm going to graph again, and I get my 0.7, and I do get another function that is looking like something. It's hard to see because it's way over here, but I'm going to go ahead and do the intersection. So I'm going to do second calculate, go down to the intersection and let the calculator figure it out. So I'm going to hit enter, and am I on the first curve? Yes. Am I on the second curve? I hope so, because it's hard for me to see. Would you like me to guess? Yes, I would like you to guess. Okay, so it's guessing, calculating, and it says error, no sign change. Okay, so that we have to think about for a minute. What does that mean? Well, I just found something very interesting. You have to be very careful about how you set your window, because I had set my window to a standard window of negative 10 to 10. But my point of intersection is at 60. So when I extended my window to include my point of intersection, the calculator gave me an answer. So my problem was a window issue. I had put them in correctly. I had figured it out right, but my window did not include an intersection. And so I got a no sign change error because it was not able to calculate past the window that I had put it in. Very interesting. So always check your window and give yourself a generous window when you're trying to graph with an intersection type of a problem. So the answer is 60.198, or 60 days. And I learned something new, that your answer can't be outside of your window, or your calculator will fail and say there's no intersection. Very good. All right, so the last one that we're going to do is the last one on the PowerPoint, and I'm going to read it to you. So it says, in September 1998, the population of the country of West Goma in millions was modeled by f of x is 16.1 e to the 0.0011x. At the same time, the population of East Goma in millions was modeled by g of x is 14.5 e to the 0.0112x. In both formulas, x is the year, where x is equal to 0 corresponds to September of 1998. Assuming these trends continue, estimate what the population will be when the populations are equal. Okay, so we need to make sure this one has a definite large window for growth. Okay, so we're going to say one was 16 million to start with, and the other one was 14.5 million to start with. So we're going to make sure that we have, everything's going to be in just millions. We're not going to put all those zeros in there. So what we're going to do is we're going to take our graphing calculator again. We're going to do our y equals, and we're going to clear out what we just did, and we're going to put in there 16.1, and then our e is second natural log button, and then 0.0011x inside the parenthesis, close the parenthesis, and that is West Goma. And now we're going to do the same thing for East Goma, and then I'm going to show you what I have. So I have 14.5 e to the 0.0112 parenthesis. Oops, I forgot my x. Put in an x, close my parenthesis, and I have this in my calculator. So we're going to see what happens and graph it. Okay, so we're going to graph those two equations, and we're watching for our window. So I'm going to go through and see what the window is doing, because I'm not getting much of anything. Since this is a population problem, I'm going to erase the whole -10 thing. I'm going to go 0 to, let's go to 1,000. Okay, and then on the y value, I'm going to erase the 0 and the -10 and put a 0 to, since we're doing, I'm going to just make 100 in both directions. So we're going to go 0 to 100, 0 to 100, and I'm going to change my x scale to 5 just to see if I get something, and my y scale to 5, and I'm going to try to graph again. And now I'm getting something that is looking like something. I see a first curve and a second curve. Okay, so I think that was probably a good move on my part to make the x and y go by 5s so that I could actually see what was going on a little bit better. So my window was 0 to 100, 0 to 100 with steps by 5. And I got a graph that looks reasonable. Okay, so now they're asking me what would be the population, which would be the output, the y, when my two populations were equal. So I have to find the point of intersection between these two graphs. So I'm going to do my second calculate. I'm going to find my point of intersection, and there's the first curve, there's the second curve. Would you like me to guess? Please do. Okay, and they're giving me that it's going to intersect in 10.36 years, which wasn't the question. The question was, what will be the population? And it looks to me like it's going to be 16.28 is the y value of the intersection. Okay, so 16.28 million. And my slide answer is 16 million, because they put everything in millions, but 16.28 would be more accurate. And when you're talking about millions, I would certainly do parts of millions, right? So that is the end of our PowerPoint and the end of our 5.2. And I will be back shortly with 5.3. And this is Mrs. A, and may God bless your day.